Can you explain to us, like we are both 5 years old, Trevor, what is the moon? And I'm talking specifically, what is it made of? I think, and you can correct me if I'm wrong here, but I think it's made of cheese.
I've heard this like line all my life of people like laughing at cheese, and I'm like, I'm wondering if I like missed like a cultural reference or something like that. And like, I bring my telescope. It's from something. Yeah. But like, I'll bring my telescope into the street sometimes and have the moon on there, and I'll have my phone attached to it and be like, oh, look, it's made of cheese. And everybody laughs. And like, I feel like I'm missing out on something, just a little something. I don't know why the cheese thing is the thing it is, but yeah, what is it really? I mean, if I was to explain to a 5-year-old, it's basically kind of just a rock up in space. It's a solid rock. It's just dirt. Yeah, you could say that. If you go further, let's say you're talking to a 5.5-year-old, you could maybe bring out the example of like everlasting gobstopper. You know, do you remember those? Yes. Like the big like sugar balls, and they would take like a week to like lick open.
Oh yeah.
Great. We're a minute in and I'm already talking about licking things. All right. You lick it hard enough and you start to see sort of like all these layers around it. And you've probably seen diagrams of like when they cut a planet in half and like you see what the different layers are. Basically at the middle, you have this very solid iron. Iron comes up a lot. Iron is in the middle. It's this very solid, compact center of the moon, really.
Yeah.
Outside of that, you have this liquid area that's also made of iron. Okay. So you get this liquid thing around the solid thing. And then beyond that, it gets a little bit, you know, sludgier. Okay, it's sort of a molten layer. And afterwards, the majority of it is this mantle, which I think is also made of a lot of iron and solid rock type of stuff. And then you have the crust at the end, which is sort of like the onion skin of the everlasting gobstopper, which sounds like terrible tasting imagery. But yeah, when I do bring my telescope into the street, you'll see these craters, and that's cool. But then you see these dark spots on the surface of the moon. And I explained to people that the moon used to be long time ago, volcanically active. And so lava would come and bubble up to the surface and sort of spread out. And it makes these dark areas on the moon. And you can see it like with the naked eye. When you look at it, you're like, oh, there's like these dark spots on there. And before we had, you know, the invention of telescopes or even like good glasses, we used to think they were seas, like water seas, and we call them Maria, right. Which mare, which sounds horse-like, I think, but it means seas, I think, in Latin. We used to think there was like water seas on it. What we found eventually is actually just old lava sort of spread onto the surface of it. So yeah, short answer, it's a rock, but it does have an interesting gooey inside and old lava deposits on the top. So as I was sort of preparing this answer, I was thinking to myself, like, when I look at the moon now, it's like, you can imagine just sort of this dead rock. But then when I think inside, there's like this molten hot layer of stuff going in there. I'm like, like I'm the next time I look at the moon, I might look at it a little bit differently. There's stuff going on inside of it. So
I'm already going to look at the moon differently.
Absolutely.
Try not to think of it as a giant gobstopper, but that's it's super interesting.
I mean, I expected, you know, you to say some variation of it's just dirt or something like that. It's a bunch of sand. I don't think I expected that it was basically just an iron ball up there just to hang out.
Yeah. I mean, there's some limitations of my knowledge here. Like when I hear the word iron, like I think of like a metal beam, like an I-beam sort of thing, like with that old 1920s construction photo, whether it's staged or
on the thing. Yep,
eating lunch, you know, 1,000 feet in the air or whatever. And like I'm trying to imagine like what ore in a non like human shaped thing, what it actually looks like. I'm not sure if I've ever really held iron.
Like, yeah.
Maybe I have, and I didn't know I was holding it. You know,
I have no idea either.
Yeah. So I think
it probably just looks like a rock, to be honest.
Yeah. There is, you know, obviously I'm simplifying. You know, we got the center, the molten lava. The surface of it does get kind of interesting, especially with like, I want to say new knowledge, but new meaning like in the last 50, 60 years since we've gone there. When you get to the surface of it, it is quite powdery. So it's not just a solid thing, but it's sort of powdery on it. And we call this lunar regolith. And when astronauts went there, they found that it really was like very destructive to the stuff that they brought up. So it's very abrasive, you know, microscopically, I guess it's very, just destructive of the material. So like cloth that would get up there would get destroyed quite quickly. The metal things they brought that would, you know, work together, that gets destroyed very, very quickly. It's very, very destructive, the lunar regolith. So that's like one of the big challenges of like when we're going to be going back to the moon, which we might talk about a little bit later, is like when we went up there in the 60s and 70s, we were only up there for like, you know, at start maybe a dozen hours and then 2 days and then 3 days. And even just that short amount of time, just how much damage was done to our equipment. And now that we want to plan to stay there for, you know, weeks or months on end, we have to really think about like the engineering of our stuff up there, just because the stuff, the surface dust, the regolith is so destructive. So how many times? Well, how many times can I say destructive in 2 minutes? I don't know, 7 or 8 times.
Lot.
There.
Yeah. Well, hold on to that thought, because you already mentioned this, that we're going to talk a little bit about this a little bit later in today's episode. Listeners, welcome to another extra special episode of Geography is Everything. That is our friend Trevor Kjorlien, who is also better known maybe perhaps as Plateau Astro over on Threads, Instagram, YouTube, anywhere. It kind of feels like anywhere, you know, you find that name, it's probably going to be your handle. And I believe Plateau is spelled Plateeau, right? Is that correct?
I think I'm on a geography podcast because plateau, flat. Yeah, you probably, you know how to spell it.
There you go. Yeah, exactly. Yeah. Plateau Astro, spelled just like the geographic feature. Go check him out. Today, we are going to talk all about the moon once again. So a couple days ago, you listened to me and Hunter prattle on about the moon and sort of the geography of it, sort of the higher level, more basic version of sort of what we're going to talk about today, because now we're going to be able to dive deep into all of the things that we simply didn't have the expertise to talk about on Tuesday. And Trevor is here to help us do that so that, well, I'm not an expert on astronomy or the moon. Hunter, are you?
I'm not an expert in these things. I remember taking a few astronomy classes back in the day, but, you know, some of that stuck, but I'm here to learn. Yeah, absolutely.
I also took an astronomy class because at one point I did want to major in astronomy. And then I realized that with an astronomy degree came classes in astrophysics, which then meant a lot of math and calculus and everything like that. And it was at that point I decided maybe it's not for me.
I think you both, just to be fair, have done more astronomy university classes than I have. I think I did 2. So maybe we're tied, or maybe we're a little bit
might
of a
be
race.
tied.
I did not graduate. I did not finish university. So this is all just knowledge out of general interest and a hobby that has sort of gone out of control. So,
I mean, you certainly know your stuff based on everything that I follow on social media, which is why we have you on today, Trevor. So let's go ahead and launch into our next question for you. Let's get to the tides, right? Everybody knows the moon has an impact on the tides. So can you explain the role of the moon in regulating Earth's tides and how this kind of influences coastal geography and perhaps human settlements? Although I don't know if we can actually get to that, but I feel like that's something that, you know, has an impact there for sure.
Yeah. I guess we can sort of start with some styrofoam balls as you normally do. So yeah, the tides, like
everything.
The tides, you know, the water goes up and down, and through the course of a month, you'll get bigger variations of it. So the tides, or the oceans, big bodies of water, are influenced by gravity, by things in space. So, you know, we have the moon here. Or the moon. This is a great start answering this question. We're the Earth right here. There we go. And the moon goes around the Earth. Okay. And this takes about 1 month for it to completely do this. Now, off to the side here, you just got to maybe pretend the sun is way over on this side over here. Okay.
Far over.
Yeah. So you imagine the water that we have on the Earth right here, and the moon's gravity is tugging on the water over here. And if the sun is over there, you're sort of getting also like another effect of the sun pulling on the Earth's water. So you're getting this sort of double effect of the moon and the sun. About a week after this, the moon has moved about like this. Okay. So the moon is still tugging on the oceans. Okay. So the water's being pulled this way. Okay. But it's also being pulled this way from the sun. So what we call this is called a neap tide, N-E-A-P, neap tides. So you're not getting really much variation in tide at all. It's getting pulled here and here. It sort of kind of like almost cancels each other. Yeah. About a week later after that, we get the full moon. Okay. And so the moon is pulling it, the Earth's oceans this way, and the sun is pulling it this way. And then we get a little bit more tugging of it. It's not being canceled out like it was the week before. Okay. And then a week after, okay, we're third quarter moon here, getting pulled this way and this way. So it sort of cancels each other out again. And here it's a new moon. Okay. So we're getting pulled from the moon and from the sun. So here is where the oceans are being pulled the most at a new moon. Okay. Here at a full moon, a little bit less, but these 2 points here at neap tides, when it's getting pulled here and here, that's where you don't get really the high tides at all. So that's sort of like a little bit of a backgrounder on like what is actually going on with that. I remember, sorry if I'm rambling here. I remember being in Australia and I was staying in hostels. I was in my early 20s and somebody told me, and this is before I was really super into astronomy, saying that the phase of the moon affects the tides. And I was like, how could that make a difference? Like, how could the difference of it looking more lit up or whatever make a difference on the tides? I didn't believe it when I was in my early 20s. And it wasn't until I did my first astronomy class after I went to university that oh, okay, that makes sense. Where the position of the moon is, that actually makes a difference. So, I mean, the tides, like along the coast and stuff like that, you're going to get different variations of how high the ocean water comes up. And that is going to affect, what animals, how far they get up onto the shoreline. It's going to affect how close we actually want to build to the oceans as humans, so how we want to settle there. And so, yeah, that's sort of how the moon affects the tides in our settlements here on Earth.
And you're located you're located up in Canada.
Yep.
You're located not too far away from some place called the Bay of Fundy, correct? I mean, you're not super close if I'm remembering correctly, but it's sort of over in that, Nova Scotia area?
Yeah, that's still pretty far. I've never been. I can't drive there this afternoon, basically. Well, I know what you're referring to. Yeah. And
the point I'm trying to make, you see those videos of the tides, and I think it's considered to be one of those places that has one of the most dramatic tidal shifts for some reason. I have no idea why, but you can see videos of this where there's an area that is completely full. There's a bunch of boats on it, and then all of a sudden the tides go out, and now there's no more water at all. Like you can just walk straight across. All the boats are on the now muddy ground, I'm assuming, and it's kind of wild to see how much of a tidal influence there is, and how it's almost like why did you build boats and docks here? Because I'm assuming boats on land it's not good for a boat. I don't know.
Right. It's so I grew up in Western Canada, Alberta. I'm on a geography podcast. You might know the province of Alberta. It's just above Montana. Basically, it's very inland. Like it's prairies and stuff like that. And so like my connection to tides is extremely theoretical. Like I guess I traveled in Australia for about a year, so maybe that's my connection. But even then, I was early 20s, hostels, and just generally being kind of silly in my early 20s. So I wasn't really noticing it too much. But like, yeah, so like I still have like a very not farm brain, but like a very land-based brain. Whereas other people you meet who live on the coasts or like live, near the oceans, they have a lived experience with the tides. Yeah. And like I do not have that type of brain. That's just not where I've grown up. But yeah.
I will say I have been to the Bay of Fundy when I was a kid and saw the tidal bore, I think they call it. And, usually when you see a tide coming in, it takes you a minute or two to realize if it's coming out or coming in. But this is just water, like almost rushing in, and the change in it's a super dramatic change in depth. Yeah, it was very, very interesting, kind of a strange phenomenon, but it was fun to check out, certainly as a kid.
Yeah, man, you can't spell fundy without fun. So yeah,
putting the fun in Fundy.
Yeah.
Trevor, I have another question about how the moon affects the Earth. And so the question is, how does the moon's gravitational pull affect Earth's rotation and axial tilt? And what implications does this have for our climate and weather patterns?
Yeah, I'll break that down in a few different sections. So yeah, so we have the Earth, of course, okay, and it rotates once on itself about every 24 hours or so. But the moon does affect the rotation rate. So the moon is slowing down. Why am I mixing this up? But the Earth is slowing down its rotation. Very, 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 very small amounts. It's about 1.7 milliseconds per year. No, per 100 years. Yeah, every 100 years. Wow. It's very little. It's extremely, extremely, extremely little. Okay, it's not that much. So on a human time scale, like we can basically say that like a day on Earth will be about 24 hours. But from what I've read and seen is that like if you take that time far enough back in advance, say like around the times of the dinosaurs, 250 million years ago, that 1.7 milliseconds per 100 years builds up, and the Earth's rotation probably would have been a little bit faster, probably about 23 hours per day for it to do one rotation. So the moon affects that by going around it and sort of slowing the rotation of the Earth a little bit down. The moon is getting a little bit further away as well. Again, it's like an inch a year, that's not too much. But you sort of build that up over hundreds of millions or perhaps a billion years here or there, geological timescales, and you can notice the difference. So right now the Earth is sort of slowing down a little bit because of the moon. The question was about axial tilt. This, I love bringing this up. So I came prepared, of course, and I have not just a flat map. I don't know what projection this is. Probably Mercator. I don't know. But we have a globe right here. And the thing that I really love showing people when I bring out a globe is showing that the Earth is tilted. I thought for the longest time that like every globe was like broken in some way. It's like, why is it tilted this way? Like, is that just a design flaw? It's like, no. The Earth is not like this. It actually is like that. So it is tilted by about 23.5 degrees. And that tilt is what actually causes the seasons here on Earth. Mm-hmm. Without that tilt, we wouldn't have that variation in summer, winter, and spring. Without the moon, I'll rephrase. The moon helps to stabilize this tilt. Okay, so the tilt is constant, basically in our lifetimes and for millions of years. It'll always sort of be about 23.5 degrees. If we didn't have the moon, this tilt would actually wobble quite a bit. It would actually be quite unstable. So instead of it being 23.5 degrees consistently, it would be quite wobbly. And the Earth does wobble a little bit, but it's very, 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 very little. So over the course of, I don't know, hundreds of thousands of years, it'll wobble a little bit, but because the moon is there, it helps to stabilize the tilt of it. To give sort of a counter example of it, I was just researching beforehand. I was thinking about Mars. And Mars also has a tilt. It's about 25 degrees. It's like kind of really close to Earth's. But Mars has two moons that are both very, very small. And if I've read it all correctly, it does wobble about like 10 degrees every 100,000 years or so. So that's actually quite a bit of wobble for a planet like that. And so if you take 100,000 years and you think humans have been around for about 200,000 years, something around
like
there.
That, yeah.
I got two academics here. They should be able to answer this. I don't know.
I think we'll just say that's probably right.
Yeah. That amount of time, like in a human lifetime, would you really notice a difference? Probably not. But on the lifetime of like a species and that tilt of your planets and ice ages and other different variations in temperature and climate, that would probably make an impact. So I'm sorry, I give really long answers. so the moon basically stabilizes the tilt of the Earth.
Trevor, so I think you're leading us right into sort of what our next question is, because we're going to keep talking about a little bit about the climate and the moon's impact on it. But you're sort of already hinting at this. But so the moon, it seems like it contributes a fair amount to the seasonal stability, let's say, of the planet, right? Because without that, you were talking about the wobbleness, and I don't know exactly what that would do. Maybe we're going to answer that right now. But let's say we take the moon out and it's doing this wobble thing. Would that significantly alter the seasons? And like, I mean, it has to, right? I can't imagine it not. Like, it would have to. Everything seems to be running so finely tuned to that 23.5 axial tilt degree angle that if you were to remove that aspect, things would just go wacky.
Yeah. I'll start by answering. There's a great app. It's not free. It's called Universe Sandbox. And basically, it's like a simulator of different things you can do in space. So, an example, I gave a presentation the other day to some kids in my planetarium, and a kid asked, "What would happen if the sun disappeared?" And so I didn't use this app specifically, but I hid the sun and I described what would happen and stuff like that. But in Universe Sandbox, you can actually simulate what would happen. So what would happen if the moon? What would happen? Immediately the second after the moon disappeared, you just delete it, and you can see how the orbital trajectory of the Earth would change. Then you can speed up time and see how weather systems would change on there. You can change things like the axial tilt manually if you want, and you can see over time the variation in the North and South Pole. How does more ice form at the poles, or how does it lessen and stuff like that? So let's say the moon just here we go. Got the Earth right here, and we have the moon right here. The Earth is tilted this way. And I'll just pretend this is the sun, okay? The Earth goes around the sun like this, and crucially, this is the part that always confused me for a long time. It has this tilt, but it's always sort of tilted in the same direction as it goes around the sun. So I'll demonstrate that here. So it's going around the sun like this, and it's always pointed sort of in this way. Okay? You see that there? Okay. For the longest time when I was a kid, I never quite understood the tilt thing. I thought maybe it goes around like this, or the tilt of it. Maybe that's what causes it. No. Sun, Earth, always sort of tilted in the same direction. So you can imagine here, and I do this better in a dark room with a light bulb and stuff like that. If you're here, okay, and you are on the North Pole, okay, and you're rotating like this, you're going to get sunlight. Basically, no matter how much you rotate, you're always going to have sunlight right here. Okay, so this is summertime. On this side, no matter how much you rotate, no matter how much you rotate here, it's always going to be dark. So it's just going to be cold all the time. 6 months later, when you come over here, you're on the North Pole, okay? You're not getting any light right here, okay? Okay, so it's gonna be very, very cold, okay? But on the bottom here in Antarctica, you're gonna be in perpetual 24-hour sunlight for several months. Right. So that tilt is very, very, very important. And you could imagine this, and you can play with this in Universe Sandbox. What if the Earth had no tilt? And what would it be kind of like? And short answer, it's basically like the equinox all the time, and you can simulate that. So let's just say the Earth was really wobbly like this. There would just be no real consistency. It's kind of insane how consistent the seasons actually are. You'll get variations, of course, but you can generally say okay, by end of September, what's the temperature going to be like? And you can get within a couple of degrees of guessing and be pretty pretty good. Asterisk climate change. But anyways, you can get pretty close. With a wobble going around like this, who knows what it could be like.
Absolute pandemonium. No way. I mean, I'm assuming our local weathermen would probably be out of a job, because how would they ever predict the weather in that situation?
Yeah, they would just be weather news reporters and just what wacky stuff is going to happen today. I don't know. And
What's happening today?
Yeah.
It's fascinating because, like you said, I mean, I can tell you, right now it's July 5th here in Portland. I can tell you, sometime around, October 15th, it'll probably be an average temperature of around 65 degrees in Portland. Like that is pretty well established. Maybe there'll be a, weird heat wave or a weird cold snap, something like that. But generally, right, the averages don't fluctuate that much. Again, asterisk climate change, because that's something. But you're right. Like I've never really thought about it and just how consistent seasons are, but you don't even have to look that far away from Earth to find out that, the seasonality of planets can be like, doesn't Venus have like wildly erratic weather patterns, or whatever you might call it over there, where it's just like complete chaos because it's just completely different area and they don't have the stability, or it doesn't have the stability that the Earth does.
It's really kind of fun to play with Universe Sandbox to play those out. So I won't say the client's name, but I do some contract work for some creative companies where they want to like make a story somewhere, and they want it to be kind of rooted in as much reality as they can. And so I would give them, okay, imagine a planet that is like tidally locked to the sun. I can't get super into it, but basically one side of the planet is always facing the sun. Okay. So as it goes around, it's sort of like one side is always at. So one side is perpetually in darkness, while the other side is perpetually in light. So you'd have one part that's completely frozen, another part that is completely hot. But around the poles here, it could be habitable there. So in Universe Sandbox, I'm not plugging Universe Sandbox. They're not paying me.
We are not sponsored by Universe Sandbox.
It's fun.
We'd love to be.
Love to be. Yeah, it's great. It's great. And you can sort of simulate those things. And it's a fun tool to bring into the classroom for kids, because then their imaginations just go really wild of like, what if the Earth rotated the other way suddenly? What would happen? Okay, what if it was tilted more like this? And it sort of simulates it. Kids really like destroying planets, but they also like seeing the effects of what happens when you change some of those variables and speed up time. So
I don't think that would probably be a surprise to anybody who has kids. Hunter, would that be a surprise to you?
It would be unshocking. Yeah, not shocking at all. Trevor, you mentioned a little bit earlier that the tides has some impact on, how animals can access water for various reasons. And I'm just wondering also in what other ways the moon might affect the behavior and migration patterns of animals. And then how in turn does this impact human activities in ecosystems?
Yeah, you could probably ramble on for quite a while about some of the different things. Behavior. Okay, so the moon goes through a cycle, about a monthly cycle, and you've probably all seen a full moon. So if it's a night of a full moon and it's clear out, you have this very kind of bright light in the sky. And then 2 weeks later, it's a new moon and the moon isn't visible at night during the sky. So you have this great variation between like it being very bright or very dark on different nights over the course of 2 weeks. So I don't know much about nocturnal animals, but I will say that nocturnal animals are awake at night. And I have to imagine that like the hunting patterns of animals would be different depending whether it's a full moon or if it's a new moon. For some, it might be a complete advantage that the moon is out. But for some, I don't know, bats, where they don't really see, where it's all sound, maybe having it just be
bats.
Yeah, something like that, where it's completely dark out, and that is like an advantage for them. So yeah, just sort of bring it back to that Universe Sandbox thing. Just imagine, what if Earth had two moons instead of no moon at all? If there's no moon at all, okay, there'd be a lot of chaos and stuff like that. But if you had two moons, and there was some consistency around the timing of how that would change like nocturnal life, Would it be double bright? You have darkness again, or what would the, would it weekly, would it be different, one moon here,
Yeah.
one moon there, stuff like that. Anyways, you can sort of do some what if scenarios like that. So that's sort of some behavior stuff. For migration, we talked about the tides, and I could imagine, again, I'm not a biology person really at all. So when it's high tide, does that change the migration pattern of some, I don't know, crabs or fish? I mean, probably, I guess. I don't really know. Another one I thought of is direction for migration. So if you're in the northern hemisphere, the moon is always in the southern sky. So let's say you're
I never thought about that.
Yeah. And if you're in the southern hemisphere, it's always going to appear in the northern part of the sky. So let's just imagine you're in the northern hemisphere, you're a bird and you're in Florida, okay? And it's springtime and it's time to migrate north. Again, I haven't read anything about this. This is just a little Trevor thought experiment. Is like, okay, I'm a bird. I have to go north. If it's a full moon out, do I know instinctively as a bird that like I should be flying in the opposite direction of the moon? Because I know that the moon is south. Like, should I be avoiding that thing in springtime when I have to know where I'm going? Again, this is just Trevor thought experiment here. And then conversely, in September, October, autumn, when it's time to go back south, do birds recognize that like, oh yeah, the moon is always in the southern part of the sky. So when I'm flying, do I like fly towards that thing? Just a guess on my part. Like,
I could definitely see that being the case. Yeah, I will. I mean, I would imagine there's a lot of reasons. I mean, as with everything, we talk about this all the time. There's so many different reasons for why something happens and why animals or people or whatever sort of settle where they do or move in a different direction. And it's like, yeah, the moon has been there throughout this entire species' life, right? Let's take Canada geese, for example. Has been for as long as Canada geese have been around, that moon has been in the sky. And so I have to imagine, there's got to be some impact of seeing that moon and sort of helping with the directionality. It's probably not the only thing, but I would not be surprised at all if your Trevor thought experiment had a little bit of truth to it, because how could it not? It's such a constant. And I think that's what you find in nature is like the constants are what guide so much of how and where, people and animals move to.
Right. Yeah. Asterisk. This is not a fact. This is just Trevor thinking out loud. And perhaps there's some research done on direction of moon and bird migration. But I think you're starting to think about, position of the moon. And yeah, hopefully that sort of gets you sort of thinking about.
Well, Trevor, let's leave biology behind. None of us are biologists. I appreciate you helping to explain the moon aspect of this, and we can sort of riff on that. But let's move that behind, leave the biology behind. Let's get to another question. What are the potential impacts of future lunar exploration and potentially colonization? And how does that change sort of the geopolitical landscape on what's the big deal? Why are we doing this? Why do countries want to do this? Why does China and the United States and maybe Russia too want to put a moon base up on the moon?
Why do we want to do that? Yeah, that's a good question. Yeah. I mean, why do we explore? I won't get philosophical there. So we'll take a step back. So in the late 60s, early 70s, America went to the moon. We were only on there for a couple of days. Like, I think the longest mission was 2.5, 3 days, Apollo 17. And the question I get all the time is like, how come it's been 55 years since we've gone back? Do we like not have the technology anymore, et cetera, et cetera? The priorities kind of shifted to learning how to live long-term in space. So during the 80s, 90s, early 2000s, 2010s, we've basically been trying to learn how to live like 3 months, 6 months, a year at a time in space. And the way we've been able to do that is with the International Space Station, which you might have heard. It's like an orbiting laboratory. It's been up there for 26 years at this point, something like that. And there's humans there right now. I think there's 9 humans on top of it, inside of it right now. And they do 6 months missions. Like, that's routine now that people live there. Going back to the moon, lots of reasons to do it. Using it as sort of a launch pad to go to Mars, which then begs the question. I'm not sure if I'm using that phrase right. It demands us to ask, why go to Mars? Which is another philosophical, why go to a hellhole like Mars? I mean, it spurs development of, industries here on Earth. It spurs an economy. There's a lot of national pride, international pride within it. So yeah, the plan right now is we have people going around Earth, the International Space Station. The ultimate plan is to probably have a base there. I'm going to bring this to geography just for a moment. And I'm sorry if this question that I'm answering feels like I'm answering it in a bunch of different ways, so I apologize. But if you look at the landing spots on the moon where humans are, so you have the moon, all of the landing spots are sort of on the equator of the moon. Apollo 11, Apollo 12, 14, all around there. Where we want to go ultimately is to the South Pole right here. Okay. And this is where we want to build bases. This is where all the countries in the Artemis Accords and China and Russia, that's where they want to go. We couldn't go there in the 70s, 60s and 70s, just because it was just orbital mechanically, it was just too difficult to get there. But now we're building better systems so we can actually get there. And the reason we want to go there is supposedly ice, lunar ice there in the lunar regolith. There are craters there that never get any sunlight at all. So we think there's water deposits in there that have been frozen and just frozen ice there. And if you have ice there, you can turn ice into water. You can separate that H2O into hydrogen and oxygen and use it for fuel, which sounds a little bit, okay, can we actually do that? I don't really know. But ultimately, that's where we do want to go. Is we want to go to the lunar South Pole and set up a base. I think I've answered or not answered your question there. So maybe you want to pipe in here with either a follow-up or a question so you can save me.
Yeah. Let me shift this a little bit. So Hunter and I constantly talk about sort of, at some point or another, we talk about the colonization of various parts of our planet from European powers. And in that, we talked, let's take, for example, our episode on Easter Island just from a few weeks ago. We talked about how so many of the early European colonizers came by, would claim it, realized that there's not really anything for them to exploit, and therefore they would move on without doing too much to the actual people who are there, the Rapa Nui. So I guess what I'm trying to get at is what's on the moon? Why does in the history of colonization, the history of humans trying to go out and do something, it's always been with the aim of exploitation. Let's go up there, let's get all the resources because that's going to make us a lot of money back home where we're from. And is that up there on them? Is there something up there on the moon that they can exploit and potentially mine? And I have no idea. It sounds like maybe iron.
I mean, we got lots of iron here, so I think we're good. Honestly,
we're good.
It is that.
Out.
Yeah, we should be all right. Yeah, it is that ice. That ice is probably the big part. Because if you can have your own, what they call it, in situ resource utilization. So basically, it's very expensive to bring stuff with you into space. It's just hugely expensive. It's very heavy and all that. So if you don't have to bring it with you and it's just there, that's good. That makes it a lot cheaper to build your base there. If it's just sitting there and you just melt it, clean it up, use it, drink it, turn it into fuel or whatever. So that's probably the biggest thing. You might have seen the movie, Moon with...
Yes.
I forget. Yeah. The premise of that movie...
Sam Rockwell or something?
There we go. Yeah, Sam Rockwell, yeah. And he's there and they're basically mining, I think, helium-3. I think that it's a great movie. I think in the real world, helium-3 is exploitation there. That's not really a viable use case. It's just a very expensive way to get helium-3. But that frozen ice there is the big draw.
Gotcha.
Yeah.
Trevor, a question about lunar eclipses. So can you tell us a little bit about how lunar eclipses occur and what studying them will tell us about Earth, Moon, Sun relationships and maybe some of the Earth's own characteristics?
Yeah. So there's a few different types of eclipses. There is a solar eclipse, which we just had here in Montreal. I'm not sure if you can see. I can shift this a little bit. I worked with an illustrator to make a poster and postcards.
That's awesome.
Very cool.
Ago. It was a huge event. It nearly killed me, but we got it done. So it was good and it was clear. So a lunar eclipse. Lunar eclipse is we have, and I'll do this. I know I have limited space here. So we have the sun here, and then we have the moon. And the sun, we have the earth, and we have the moon here. So the sun's light is coming this way, okay? And all three of them are perfectly lined up, And so the shadow of the earth is blocking out the moon. So this happens on a night of a full moon. The shadow of the earth is blocking out the moon. Now, if you have ever seen a lunar eclipse, the moon turns a certain color.
It's like reddish brown or something like that.
Yeah. Why is that? Why is that? Yeah. So the cause of that is we have the earth and the sun's light is coming through here. Okay. And the sun's light is going through the atmosphere of the earth. And when light goes through a medium or air or atmosphere, it gets scattered. Okay. So light is made up of Roy G. Biv, colors of the rainbow. Okay. The blues and the greens, they get scattered. Okay. The yellows, they get scattered. The oranges, they get scattered. But the red is able to pass through the atmosphere and actually go through and go through the atmosphere, continue going through space, and hits the surface of the moon. That's kind of the basics of what a lunar eclipse is going on. So it's passing through the shadow of the earth and turning a red color because the sun's light is passing through Earth's atmosphere and making it cause to appear like a red color.
That's a little more common than a solar eclipse, right? A lunar eclipse, I feel like, is not that rare.
They both happen at about the same rate. About it goes through cycles, like say every 6 months or so. Mm-hmm. But with a solar eclipse, they happen in a very narrow part of the earth. So maybe some of your viewers in the States or Canada, they might have been in what we call the path of totality. And if you're within that path of totality, it's very kind of thin, only like 100 kilometers or so wide or so. You'll see it. So not everybody sees it. With a lunar eclipse, it happens over a much larger region. More people can see it. So we sort of get this effect of like, we think it's more common because more people are seeing, because it's happening over a larger swath, or it's more visible from a larger swath of the earth. But solar eclipses, you need to be in a certain area to do it. You said you're from living in Portland now. Yeah. Were you there in 2017?
I was. I had just. So it's funny we're talking about solar eclipses now because we did an episode for the solar eclipse as it happened. Okay. We're talking about the geography of it. So we talked a lot about sort of the 2017 solar eclipse because that's where Hunter and I are most closely geolocated to. Mm-hmm. So it was 2017. I was fresh out of grad school, had my very first big boy job, and I unfortunately had to work that day. And so here in Portland, we were like 99.9% of the way to totality, which apparently is not close enough, Trevor. Everybody tells me that I did not experience it. So close, but no cigar for me, I guess is what I'm trying to say.
Yeah, no, same experience. And then the people who experience totality, they're sort of operating on a different level now. It seems like they almost feel sorry for you. It's like, I have been, the secrets of the universe has been revealed to me, and I'm sorry you missed it, kind of thing.
Yep. Yeah. We could talk at length about seeing a solar eclipse. I'm not gonna do that. The second part of your question there was, what does this tell about Earth's own characteristics?
Yes.
Like the one thing interesting that I could sort of do that is using a lunar eclipse. Back to lunar eclipses now. And I mentioned that during lunar eclipse, the Earth's shadow is blocking the moon. So when you see a lunar eclipse, you see the moon, and then you sort of see like sort of this like bite being taken out of it by the shadow of the Earth. I can't get into the math or the history of it all, but we could have used that shadow to figure out the size of the Earth. and the size of the moon. If you can measure the size of the Earth, and actually we could have done this. Sorry, I'm as I'm speaking out loud, I'm answering the question here using the Eratosthenes experiment. Does that ring a bell? Okay,
Not for me, no.
Yeah.
Basically, it's being able to figure out how big the Earth is. So we have the Earth here, and let's say you're at the equator. Okay, you're at the equator, and you have a stick going up like this, and the sun is directly overhead, and there's no shadow being made by that. Okay, there's no shadow. But if you hire somebody to walk, a couple 100 kilometers north of the equator and have a stick the same length, and at the same time you both measure the length of the stick, and they're a bit more north, so they're actually going to have a shadow for theirs, you can actually measure the size of the Earth. There's a great Carl Sagan Cosmos clip where he explains this much better than I do. But basically, you can use some primitive tools and walking distances to figure out how big the Earth actually is. And I think this experiment was first done early AD or just before BC, 200 BC, something like that. So we knew how big the Earth was for quite a while. I mean, they had a pretty good estimate of how big it was. So if you know how big the Earth is, you can, during a lunar eclipse, see the shadow going across the surface of the moon, and you can then use the size of the Earth that you've recorded to see how fast the shadow is going across and get a sense of how big the moon actually is. Again, I could probably ramble for a long time, but I don't know the history too much about it. But using one measurement in space, you can find out the measurement of another thing. And then from there, you can measure out, okay, how far away is the sun? It's interesting how you can sort of build off of these pieces of knowledge because you know how long the length of a shadow of a stick is. Yeah.
That's incredible. That's incredible.
Yeah. Yeah. I encourage you to please Google lunar eclipse, measure moon, Earth. I may have gotten some of the little facts there wrong, but there's interesting essays on there about how that can be done.
Well, let's shift gears a little bit and talk about sort of the magnetosphere of the Earth. So, I mean, I feel like this has been in recent news. There's always like a solar storm. And it's like, I feel like every couple of years, it's the biggest solar storm to hit Earth ever in the last, 2 million years or something like that. Yada, yada. So the Earth has a magnetosphere. How does this interaction and the moon protect our planet from, or does the moon have any sort of impact on this interplay between the magnetosphere, the sun, solar radiation, and does it provide any sort of protection, or does it even have its own magnetosphere? I guess I have a lot of questions around how the moon factors into this sort of equation here.
Yeah. So I'll shotgun answer a few of these. Okay. So you mentioned the cycle of like solar radiation, stuff like that.
Yeah.
So back in May, about 2 months ago or so here, we had a big Northern Lights Aurora Borealis display here in Montreal, maybe in
we had friends. Yeah. We had friends over I had some friends over on the coast where there was less light pollution, and just amazing pictures that they had of basically, I used to live up in Alaska growing up. So I've seen the Northern Lights, and I would say the pictures that I saw it reminded me of just how bright it can be. Sometimes up in Alaska, the fact that it was this far south was really incredible.
Yeah. In Portland, we couldn't quite see them with the naked eye, but if you took a picture, it would capture some of the Northern Lights, which was pretty dramatic. Yeah.
So that was a pretty rare event. So the last time that we had sort of a solar storm like this was about 2003, 2002, like that. So a little background on this: we have the sun, and the sun goes through about an 11-year cycle of being more active, basically. So we are pretty much at the peak of that cycle right now. So if you look at the sun through a telescope that has a filter on it, you can actually see more sunspots on it.
Mm-hmm. Okay?
And so it's just more, magnetically active. And so it's burping out this sort of solar flares sort of stuff.
I like that phrase, burping out.
Yeah. Anytime I can introduce vomit into my outreach. Yeah. So basically we're getting more solar activity, more aurora borealis right now. So, 11 years ago, that would have been 2013, and then 2002 and stuff like that. So there is a cycle. There is a cycle to it. And this one is particularly strong. The reason why we see Aurora Borealis is, as you mentioned, the Earth's magnetic field. So, we have these polarity going around the Earth right there. And when the particles from the sun interact with the magnetic field there, like I said, excites the particles. Again, sort of the limit of my knowledge here. We get that wonderful displays like that. Mm-hmm. The magnetosphere is sort of this big sort of invisible sort of protection layer around the Earth caused by Earth's magnetic field. And it's quite large. I forget the exact distance, but it's quite large. The moon doesn't seem to really affect it. If it does, it is extremely subtle. The one way that the moon might sort of interact in this way is if we have the sun. Okay, how am I going to demonstrate? We have the sun and it's burping towards us. Okay, here, see if I can do that. So sun is burping towards us right here. Okay, it's about to hit us. And the moon just happens to sort of be in the right sort of orientation that it's sort of blocking some of that. I'm going to say it, vomit coming from the sun. To my knowledge, that's sort of the biggest effect. I think they call it the lunar wake, where it's just kind of in the way of it. As far as the moon actually affecting Earth's magnetosphere, I don't think it has that much of an effect. I always love when I come with this, like, it's a really good question. We're going to talk about the magnetosphere, and I love it when I ask this to somebody who knows what they're talking about. They're like, yeah, it doesn't really do anything. No, again, asterisk, somebody who knows what they're talking about. So I encourage a little bit more research on everybody's part there. So yeah.
Trevor, can you elaborate? You mentioned a few things, but on any observable effects of the moon on the Earth's atmosphere conditions, such as weather patterns, atmospheric tides, and how these might affect human life?
Yeah. So we talked at the top of the show how the moon affects the tides, the ocean tides. Apparently, the moon does also affect the atmospheric tides. I'm not sure if that's actually a term, but
I guess the jet stream.
That may be. I don't know that specifically, but I think it does sort of affect that as well. So you can get variations in certain levels of the atmosphere based on the phase of the moon. I'm sure it's a complex interaction between different layers of different things. The ionosphere, which is another layer in Earth's makeup of different layers around the Earth, also does get affected by the moon. So maybe like a practical real world example is if you're into ham radio, let's say, and you're trying to like bounce signals off of the ionosphere, that would be affected by the phase of the moon and where the moon is in relation to it. So I think it's not as sort of direct as it is with the tides, the ocean tides, where that is very extremely measurable, like even noticeable from like a human point of view. We talked about the Bay of Fundy. It's like you're there in the morning and the water's really low, and then you get there 6 hours later and it's really, really high. That is super noticeable. Whereas I think like more of the atmosphere stuff, that is a bit more subtle. Yeah, if everybody had a weather balloon, maybe they could all measure it themselves and stuff like that. But I think there is a measurable effect. Yeah.
Well, Trevor, one final surprise question, but it's probably going to be a really quick one. Maybe you don't even know what this is. Are we ever going to have a space elevator? Is this a thing that's actually real? I've heard about this. I've heard about this being a thing.
So last year, there was a conference here in Montreal, and I had to host a panel, and I have the tote bag somewhere here. It was like a interstellar symposium. Interstellar space symposium. And basically it's I think every 2 or 3 years a bunch of big space eggheads get together and talk about like, hey, what would interstellar travel like look like? And these are like legit people that they do say that they've had to sort of really filter out over the last couple of decades, the wackos and the people who are actually legitimate, because you will get those in the early years, but like I think they've actually filtered out, so you get real people who are actually talking about this sort of stuff. And so there's proposed missions about, if we put a bunch of lasers on the Earth and we put it at a sail, how fast you could that thing, how much percentage of the speed of light. There's legit research being done on this, not by many people, but enough to fill an academic room full of 500 people and bring them to a panel. Okay, so it is happening. As far as space elevator, there were some people talking legitimately about it. There are a lot of logistical hurdles for it. Obviously, the expense for it would be very, very, very huge.
Did you say astronomical?
I purposely did not say that, but yes, indeed. But I mean, theoretically, it's all in there that it could actually work. I read a Arthur C. Clarke, if you know Arthur C. Clarke, novel about it called is it Fountains of Paradise, I think, and it goes through the process of how would you build it, where on Earth would you build it, who would be funding this thing. Just to give a brief, we talked about geopolitical stuff there. If you were going to build it, you would probably need to build it around the equator. And how many countries are on the equator? You got Ecuador, you got some in South America, some in Africa, maybe around Indonesia. Okay, there. Those places would become, huge places where you'd be shipping stuff there and getting it up there. It would change the geopolitical scene quite a bit if you could get stuff into space very, very cheaply. So it's just a fun thought experiment at this point. Though, I mean, the physics of it is sound, but I think realistically, it's like, probably not in our lifetimes or our children's lifetimes.
Sorry, I don't know if you've ever been caught in an elevator before, stuck in an elevator. It's happened to me a couple times, and I get kind of claustrophobic. And one time the fire department had to come and use the jaws of life to get us out or something. So I'm just imagining how traumatic it would be to stuck in a space elevator. I think that would be really trying. I think.
I don't think the fire department's going to save you in that situation.
Elevators can be extremely fearsome. Like you get it and you're like, where am I right now? And you're seeing that the numbers add up, especially in a tall building. Like, okay, 30 seconds ago I was on floor 4 and now I'm on 76. And like it's almost like being in a plane. And if you think too hard about it, you can really give yourself a panic attack. Yeah.
And how many buttons would there be? I mean, Empire State Building has 100 or something like that. I'm just not sure. Yes, some kid comes in and pushes all the buttons, and on the space elevator, that would be really annoying. I think.
I think you only have 2 buttons: ground and space.
Basically,
that's true. Unless there were stops along the way. Yeah,
yeah. I think it'd have to just be up and down. That's basically it. So,
well, Trevor, this has been so fun exploring the moon, building off sort of our episode earlier this week. You provide a lot of really helpful context to really just ground a lot of what we were already talking about earlier this week. Where can people find you if they want to find you elsewhere on the internets out there?
Yeah, I would probably just Google search Plateau, as in flat, okay, and then Astro, as in there's no other way to really spell Astro. So Plateau, Astro. So I'm probably most active on Instagram, seems where I put a lot of most of my content, but I'm also on Threads and Facebook, and I do have a YouTube channel that I make some videos here and there, but some are already there, but we're having a baby in September. So that might go a little bit quiet on pretty much everything for a while, but I do encourage you to still.
Congratulations.
Thank you. Thank you.
Congratulations on that.